Welcome, everyone. We shall now do some exercises that relate to the second introduction lecture, or not even introduction lecture, the second lecture by Eli, or Eli. I'm not sure how he pronounces his name. These are the exercises, and the first one is to make flowcharts for the lecture code, which is something you can download. I won't make flowcharts for all of these, but I'll just demonstrate to you how I typically make flowcharts, and probably say a few things about why is it important. It's important because it makes you understand the code better, especially if you're starting up with SuperCollider. The way we control parameters is typically by slotting UGents into parameters of other UGents. We use variables to name certain groups of UGents, and then we have the arithmetic in terms of addition and multiplication. We will go into the details of this arithmetic soon. But the crucial thing is that because the order of UGents in the code is not necessarily the processing order, it might take a while before you can quickly read code and understand the processing chain, whereas visually the processing chain is much clearer. Also, I will be producing exercises whereby I have a complex code, ask you to create a flowchart, or I have a flowchart and ask you to code it. So it will be a good way to verify the design. So that will be the other main advantage, is that when you design something and it's a complex code, then it's not necessarily obvious whether your design, your idea, is in the code, if it's translated well to the code, especially if it doesn't work. So you end up with, you know, a code that throws an error, and you have an idea in terms of what you want to create, but it doesn't even work, so you're kind of lost in the middle. Therefore, my suggestion is to design using flowcharts, because then someone with understanding of signal processing can verify that and say, okay, well, that's a useful design, that makes sense. And then if you have a design in a chart, then you can see, okay, so does my code reflect this design? And also the kind of flowchart based design is something that many people will understand, not only SuperCollider programmers, whereas if you go directly to code with complex stuff, initially you might get stuck. Okay, so I'm normally using the OmniGraffle for graphing these things. You can use whatever, you can use paper. So typically I would put a UGen in a box. So let's look at this first code here. What we have there is a sine oscillator, so let's start with that. We have a sine oscillator.ar. Sometimes I just omit the audio rate, control rate. Normally it doesn't make a huge difference. And from the perspective of making this readable for others, you might actually opt for using more descriptive terms. Because we are doing SuperCollider, I'll just use those things. Probably worthwhile, because then you get used to these names. Okay, so that's one sine oscillator. Now the frequency of this sine oscillator is 200. So the way I normally depict that is to put a little letter for highlighting which parameter am I relating to, and then typically, oops, that's not a line, and then typically I put a line as in something that highlights that there is an input. And for these, for fixed numbers, I typically don't use a box. So this would be my, I can still attach that to there. It moves around, and I have frequency 200. Okay. amplitude is 0.2, so I can do that in a similar fashion. That's called the multiplier. So the multiplier is 0.2. And then another thing which is useful is actually use some arrowheads. Makes things clearer. I mean, typically I preserve the top-down arrangement of things, so the arrows are not always necessary, but sometimes with a feedback loop or something like that, it could be useful. Okay, now phase is 0. That is a default value, so I won't deal with that. Okay, so what happens then is that this signal, so this sine oscillator, the output of this sine oscillator is called signal, and to that I add another sine oscillator, which will actually have its frequency controlled by the mouse X. Okay, so sorry, let's keep this SuperCollider E. So what I'm doing then is I'm creating an addition. For arithmetic operations, I would typically use a circle, and then this would be addition. Make it bold. Does that look cool? It's nice to have a good looking thing. Here is a big neat addition there for us. Okay, so I am adding this oscillator to another sine oscillator. So I'm adding the two. Okay, it's still going to be called a signal. And this one, what we have here is a frequency control. The amplitude is 0.2. So, oops, so I can actually potentially reuse this 0.2. Although maybe better not, because it's just a separate number. For frequency, which is now determined with a single variable, it's probably better to reuse it, but let's not do it here. I'll just grab another 0.2. So the multiplier there is 0.2. And then the frequency will be derived from a mouse X Eugen. Okay, so essentially the frequency here is that is controlled by another Eugen, which is mouse X. Okay, so mouse X controls that frequency. And then what we have is that this number, which is frequency 200, is actually being added to 200 for one parameter, and is straight controlling the other parameter of the mouse X, which is, I believe, minimum and maximum in that order. So this 200 goes plus, and then well, I can choose the letters here, maybe N and X, or I can type it out as well, minimum, maximum. By the way, I will double check that. So mouse X, min, val, max, val, great. Okay, cool, so that's that, and then to that, or actually this sum is being multiplied by another sine oscillator. Okay, so this sine oscillator, so this sum is multiplied by yet another sine oscillator, and this sine oscillator here has a specific range. Okay, so for range, I mean, what you could do is you can take another box and say range this and that, but because many boxes clog up the patch, and I try to make things more readable by using certain conventions, I typically enter the range, the maximum, on the right hand side on top. So this is 1 and there is a 0 here, which kind of visually goes for, okay, maximum of this output, top line is 1, bottom line is 0, which can be quite useful. especially if you have, I don't know, if you have frequency modulation and that's fixed, then you can do that as well. And also it's a bit easier for non-SuperCollider signal processing experts to read it if you explain it, rather than going through ranging and stuff like this. Okay, and then we duplicate that twice to make a stereo signal. That really is up to you how you do that. Maybe something like this, left, right. You can use text there. I mean, the point is that a good graph is kind of self-explanatory. Obviously, most computer music people do know max MSP. It's kind of the first point of entry for most of us. So you can kind of read it anyway, and you expect certain things to be there. Cool, so that's one, and I pretty much covered all the things here, so let's just look if there is anything cool or a bit more complex here that's worth adding in. Definitely do one with an envelope. What's happening here to the envelope used once? Maybe a situation where it's used twice. Envelope, these are essentially the same structures. Might pick that. Let's see what's further down. Similar structure. And S-play. Okay, well, let's do the last one here. See what happens. Although I'm a bit lazy to specify all the env parameters. Let's do this one. Okay. So what's the structure here? Here our signal originates from pink noise. So we have a pink noise generator. The frequency of that pink noise generator is set to 1 Hertz. No, that can't be. Pink noise, it's a multiplier indeed. Well, if the multiplier is 1, it doesn't do anything. Hello, Eli. I don't know if you're gonna ever be watching this. By the way, Eli's videos are great. I'm just saving some time because he's really thorough, and let's build stuff for community without repeating too much. So no need to multiply pink noise by 1. Now after that we send that signal into a bandpass filter. So the signal enters there, and this is the input called a parameter called input. So that's the input signal, and then there is the frequency parameter. Sometimes it gets a bit busy with these parameters. You can be creative with that, which is 800. Typically I like to specify the parameter values because then, you know, a good graph, it should be sufficient for someone to code this in a different environment. And then we have I think that's the RQ, if I remember right, which is the inverse of the Q. Sorry, BPF RQ, yeah, the reciprocal of Q. So let's just call it RQ, and then if someone is translating it and is confused, you probably have to look that up. 0.02. Also, the reason why I'm demonstrating this is for those of you who will be taking exam in this topic. It will be part of the exam to specify these things neatly. Okay, so that's the signal. Now that signal is then, multiplied by a fixed value 10. So filtered signal is multiplied with value 10, which is essentially a gain increase. And then we are multiplying it by the envelope. Okay, So let's do that the way it is shown. So we have an envelope. Well, actually we have an env-gen, which generates the envelope from an env there. I can put in env.percussive just to make this that bit more informative. Because there is a crucial difference in terms of which method of env you're calling, unlike ARKR, which I'm omitting there. env.percussive and env-gen. Yeah, and then the env-percussive has a gate which is 0. Not really fussed about that there. So that's again the essential thing there, and then it is made stereo. Just by duplicating the mono, so it's a kind of a double mono. Okay, I believe that's it then. Cool. T gate, and then obviously this gate is, I could actually do something about the gate, but it's not being triggered by a U-gen. It's actually being triggered externally from OSC messages. So I can put something like this. Okay, now one thing which is worth noting already is that this is actually maths. And if you call this A, and you have something which is A times B here, and do that and then times C, it is actually the same as A times B times C or A times C times B. So this is what we call the commutative property of multiplication. So I could actually save some space by doing this instead. Okay, so I mean, typically in max MSP you can't do this. You can't multiply more than 2 signals with a single multiplier. But in SuperCollider you can, and sometimes you may be surprised how things are multiplied, because typically we consider a multiplier to be amplitude control tool, but it's also a cross modulation tool. It is a tool that helps you change the range of a signal if you don't use the range, but you do it by scaling and offsetting. So there's different uses for a multiplier, and they can stack up, and then you realize, oh, well, wait a minute, I can actually rearrange the things there. Awesome. Cool, so that's that. And let's get on with some really cool stuff now, which is synthesizing some electronic drum sounds. And I have basic things set up here. Typically, you would have a good sound synthesized if you take care of the parameters. I'm not sure I'm going to spend too much time with fine-tuning. I'm just going to show you the general structure and then leave you to do the interesting bits. Right, so we're looking at synthesizing a snare with 2 filtered noises and 4 envelopes. Okay, so let's start like that. I won't make variable names. Worth noting, I can make variable names. Let's do variable names. You've seen the tilde variables, which are kind of dynamically or automatically assigned for you, but you can actually create your own. Let's save some tildes. So what I'll have 2 noises. Now I will have 2 different noise generators. What you will find, probably we'll get into this at some point. If you use the same noise generator multiple times, then they are strictly correlated, and that has some implications for how stuff sounds. Okay, so typically what you could try is double mono 1 noise oscillator, so send it both left and right, or have a separate noise oscillator left and right and listen to the difference. I can't show you here, it's a mono video. So I will use two separate noise generators, and I will have 4 envelopes, E3, E4, and I will have a Z, typically is the last letter of the alphabet. I use it for the final signal, so to speak. Okay, so let's start. Noise 1, pink noise, sure, AR. Noise 2, white noise, AR. Okay, and then envelope 1. Well, as you've seen it, I need an env gen to run it, which is a U-gen. It runs at audio rate. And then I need an env object, which is not a U-gen, but it allows me to specify an envelope. So what I'll probably be using is a percussive envelope. And the parameters there are attack time, release time. I'll leave it like this for now. Okay, and then that's my envelope 1. Now what I will also do is I will specify the ranges for these envelopes. So let's say this will be an amplitude envelope, so I don't need a range there, so I won't specify the range there. Only for the second envelope. Oops, how did that happen? So that's my first envelope. My second envelope will be running, let's see, cutoff of a filter. I'm making a snare drum, so let's go from 2000 down to 500. Okay, that's my envelope 2, and then I will have envelope 3 and 4. Well, this one I will make the attack time slightly longer, the release time maybe slightly shorter. This envelope will run, let's do different times here as well. As I said, I'm unlikely to play too much with the parameter values. I'll leave that to you. And this range here, now this will control the cutoff, sorry, the resonance. So and the resonance, as you've seen with the bandpass filter, typically is controlled with RQ, which is the reciprocal of Q. So Q stands for quality of the filter or sharpness. So typically if you increase Q, you make it more ringing. And here if you decrease Q, you make it more ringing. So what I would like to do is start with the ring and open up the filter from there. So I will start with ring and open up from there. Okay, so obviously I rushed ahead a bit. I've kind of coded most of it without testing anything, but it's never too late. So let's just see if this noise plays to start with. Okay, there are issues. Let's see, what have I done? Pink noise and one. Play. Did I select it badly? Syntax error, unexpected bad token. Am I using? I have a bracket problem and I have it for these. Okay, so that's a finishing bracket there. That's a finishing bracket there. That should be better. Great, so that's one noise. And then let's see applying the amplitude envelope. So times A1. What's going on here? A1, sorry, E1. There we go. Cool. And then what I would like to have is a filter that drops on this signal. So I'm using a bandpass filter, audio rate. This is the input signal, and my frequency is envelope 2. Hell yeah. Cool, and then the other one would have similarly a bandpass filter. .ar, and then the input signal here is second noise times third envelope. The frequency can now be fixed. Let's do 300, and the Q is now envelope 4. So let's listen to that one. Okay. And then the two together will be the addition of these two signals. I didn't use the variable Z. Fine. Okay, well that's the structure. Now obviously play with the parameters. Maybe you can get a neat little snare out of this. Maybe make things shorter. I would definitely distort the thing a bit, get some non-linearity in there, but I'll leave that to some other class. Okay, so that was my snare drum with 4 envelopes and 2 noises and 2 filters. Now next one is a kick drum, and the structure is fairly similar, so I'm just gonna start from that. Except I have oscillator 1 and oscillator 2, and I still have 4 envelopes. So my oscillator 1, well, it didn't specify it, so I'm free to choose. Let's have a sine oscillator for dropping the frequency, and kick drum 60 Hertz. No, actually here we're gonna drop the frequency. Okay, so that will be slightly different structure. Okay, I'm rushing ahead a bit, and then let's have a low frequency triangle. Probably won't alias because it's gonna stay at low frequency. Okay, so those are the 2 oscillators. Now the thing is that for the first oscillator, I will control the amplitude and frequency with the envelope. Okay, so my first envelope will be the amplitude envelope. I will leave that as is, but this one will be my frequency envelope, and this now has to be a frequency parameter here. Okay, so I have to define the E2 before I can use it. So this becomes the order, and then what shall we do here? Well, let's go from 1000 to 50. Okay, and then, well, actually what I can do is I can make this structure a bit more transparent. So I will first define the 2 envelopes, and then in the definition of the oscillator, I will already multiply with the envelope 1, which is the amplitude. Okay, and then for the second oscillator, I'll do a similar structure. So first one is amplitude envelope, and the second one is now filter cutoff envelope. So what I will do is I will drop that from 5000 to 100. So I will have a fixed frequency for this triangle. Let's do 70 Hertz. And what I will have is a dropping filter. Let's take a resonant low pass filter. Input signal is that triangle, and frequency now is envelope 4. And let's make it resonant a bit more. Okay, and then finally multiply that with envelope 3. So you could ask the question whether using the amplitude envelope after the filter, which is the current position, or before the filter makes a difference, and it doesn't. Okay, so the filter is a linear process. and therefore it won't make a difference. If we had a nonlinear process, if we had a distortion type process, then it would make a difference. So with the distortion, it's crucial that if you increase gain before the distortion, it does something different than increasing the gain after distortion, which we will get to in a few days. So that should be it. So, well, fingers crossed that I managed to code this straight up. Okay. Well, that goes up in frequency rather than down in frequency, so it doesn't really account for a neat kick sound. Let's try the other way around. Okay, so I think I'll play with the parameters just to make this a bit more kicky. So I need to drop this frequency much quicker. Okay, so let's try 1/10 of a second. And that's also quite slow, it seems. Now it seems that there is an issue here with the ranging of it. Okay, so I kind of expected it to know what the nth-gen does, but it seems like we have an issue. Let's poll this. Let's see what are the actual values. Okay, so that's not really doing what I've expected it to do, which is sad. Nevertheless, useful, bit of debugging demo. So how do I do this? Well, let's forget the range in that case and see what values I get from here. So the thing is that I'm dropping to 0 and from 1. It seems that's kind of the likely thing. So what I can do is I can do my math here manually. So typically if you do range conversion, so you change the range of a signal, you multiply and add, and you could do add and multiply in the inverse order, but it's slightly easier to understand and predict the final range from multiplication and addition. So the easiest way to think of this is that the multiplier changes the scale, so the distance between minimum and maximum, the range of the signal, and then the adder plus value offsets it, so puts it up or down, but the range stays the same. So typically you would first fix the range. So let's say I still wanted to go, what was the original one? I don't even remember. Let's say I want to go from 1000 to 50. So my range then is 950. So the difference between minimum and maximum is 950. And my original range is 0 to 1. Target range is 950. So I have to multiply by 950. In which case I will get a signal that runs between 950 and 0. And then if I add 50 to that, I will get a signal that runs from 1000 to 50. Okay, so let's just pull that as well. I did it in the next row because otherwise I would have to bracket around it all, because as I said in SuperCollider, the math precedence does not hold, so you go in order, first, second, third, but the method call dot something has precedence over math. So if I put here 50.poll, it would actually just be polling the number 50. Okay, so let's verify that. Okay, so it does seem like it's gone down to 50, and indeed this is a bit long for me. All right, cool. So that's my kicky oscillator number 1, and then let's listen to oscillator number 2. Now obviously I can now predict that the nth-gen does not work with range, so what I wanted is 5000 to 100, so the range there is 4900. I multiply by that, and the other is 100. So what you will note is that the minimum range, if this is 0 to 1, original range, then the minimum of the target range will actually always be the adder. Okay, let's listen to this one. Okay, and then the sum of the two, O1 plus O2. Great. I'm not horribly excited by this kick drum, but obviously if you set the parameters, play around with this, you might get something more to your liking. Great. Cool, that's number 3. Number 4. So what we want to do here is synthesize impact clicks using parallel filtering. So what you will get with the kind of electronic drum synthesis is that typically there is a click sound at the beginning. And actually another thing which is often used is starting your sine oscillator typically at a non-zero phase. Okay, so that's another way, because if you understand, the sine starts from 0, goes up and down. But if you start it from a non-zero phase, then you'll get an initial click, which can be useful. Now obviously I'm enveloping it here, so that click would be kind of obscured. But experiment with that. You might find that if you have a clean sine wave used as a kick, the starting phase will dramatically change the sound. Okay, so now I'm looking at synthesizing impact type clicks. Trig.ar is a lovely UGen that creates a fixed duration click. So let's check that one out. So what it does, oops, not poll but plot. Trig AR, what am I missing here? Oh, it's too long. It was fixed at 1. Okay, so that's what it did. So for 0.01 seconds, it is outputting value 1, and then it drops immediately to 0. So you can listen to this. Sounds something like nothing. Please. Did I hear anything? It's a very, very faint take. Let's try to exaggerate that. That's more of a click. Okay. So the task here was to use parallel filtering. I'm kind of thinking, shall we do a bit of triggering magic here? Let's play a bit with this trigger. Let's try to create a kind of a bit that goes up and a bit that goes down. Let me just see if I can specify the duration of the plot here. I'm not sure about this one, to be honest. So let's just do it in micro time, and then we can increase that. So let's just see if we can kind of concatenate a few triggers. Now, the trigger has an input, which is the trigger, and it should trigger when it goes from 0 to positive. So what I would think is that if this is my trigger A, I might be able to create a B trigger, which actually takes 1 minus the A trigger as its trigger, like that, in order to delay it for that amount of duration. You see? So now the ending of this trigger has triggered this one. And then what I could do is I could inverse that one in the sum. So I can say, let's take trigger will be, or actually let's call it impact, is trigger A minus trigger B. Okay, so what I've done here is created a kind of an up and down type trigger, and the useful thing is that this will be a louder thing. Let's see, maybe I can even hear the very short one. I can hear it slightly better, that's for sure. And then I can also play with these values as well. I can make this something like that, this make it something like that. Okay, so I get more of a pulse. Now this, I did hear the 2 clicks there, so I'll make this slightly shorter. Let's see. No, it's a bit long now. How about this? Well, let's use that. Okay, so bless me. Parallel filtering. So you can make an array of bandpass filters. We're gonna make an array of stuff in the 5th exercise. So I'm gonna leave that. And instead show you the Clunk, which is an array of filters. And the first thing is specifications array. So it's list of resonant filters. So what you do is you put an array as the first argument, and in that you have a set of frequencies and set of ring times. So what I'll just do is I'll randomly generate these things. Okay, so I will say array dot, I believe there is a random thing for the array. Yep. So size, let's do 5 values. Let's do minimum 100, maximum let's do 2000. So this will be my frequencies array, and then my ringing array will be something similar, but I will take from 0.5 to 2 seconds. So then I can do here something like, I hope I can, F nil in order to use the default, and R. And then the second parameter is the input, which will be the impulse or the impact sound. Okay, fingers crossed. Nope. And the reason is that I'm not making this fixed array. Would that help? No. I'm afraid that this, there is an issue here. I completely forgot the term. How are these arrays called? There we go. Ooh. Great. So probably overdriving this a bit. Let's just there we go. And then obviously if you want to make this more useful, you might not want a cowbell sound. Let's do something like this. Seems like it's still overdriving a bit. The clunk is really loud. 005. I didn't hear that. That's too many periods over there. Whatever. Okay, so that's that. That's the structure. You can play with it to your liking. Literal array. That's the term that I briefly forgotten. Briefly, did use it for a year or more. So this is a literal array. I won't go into the details. I probably don't even remember all the details. But the point is that this is not an array that you can dynamically change. So you have to make it literal, which kind of unpacks it in place. But if you look at the UGen parameters, you actually have frequency scale, frequency offset, and decay scale. So you can have a real-time adjustment of these values, but for the array as a whole. So you can stretch the array with a frequency scale, you can move it up and down with frequency offset, and you can stretch the decay also. So there is some dynamic potential there, but not in terms of creating these numbers. And anyway, the creation of arrays in a UGen like this will happen only once when you start this function. So that's that. Cool. And then finally, let's use random arrays of oscillators and filtered noise and hope to get something like a cymbal. Okay, so well, I'll cheat, obviously, and let's use the Clunk as the array of filtered noises. And then instead of I, what I will have here is white noise.ar. And this is a good chance to actually see whether I can hear the difference between using the same white noise and multiple white noises. So let's first make sure that this plays. Great. So, well, it will be, it's difficult because I'm randomizing all these things, so I won't quite get to compare. So I'll just leave that. I don't want to take too much of your time. So I'll just leave it like that. Now, definitely I will need an envelope there. Let's do that. Let's not do it in place. Let's keep it nice and neat. So my input signal here will be a white noise times env gen kr env dot percussive, and then a bit more generous with the times here. Let's do 2 seconds. Okay, so that should be, oops, that. And then you can ask, well, does that get close to Cymbal? I mean, we can play with these things. Let's I think Clunk is fairly pitched in terms of that, but it's fairly noisy. Well, let's just try what happens if I have 15 instead of just 5. The rest should be fine. Okay, 15. Okay, so one thing you might notice or think of is that I'm choosing a random value between 100 and 2000 in a linear fashion, which means that let's say half of this range is at 950. Am I saying this right? 1050. So it's equally likely to have something below 1050 and above 1050. Now, above 1050 to 2000, it's roughly an octave. But between 100 and 1050, it's about 4 octaves. Am I saying this right? 2 to the power of 3 is 8. No, it's about 3 octaves. It's just about more than 3 octaves, okay? So I'm not going into the linear exponential thing here, which I will go into in a later video. So let's think of a quick hack. How could I make this actually scale exponentially, meaning that I will have equally distanced oscillators, or actually filters in this case, and not have them all, not have a bunching for the low frequencies. So the way I can do that is by taking this to the power of 2. Okay, so I can actually induce an exponent there. And then obviously I would have to change these values because to the power of 2 they will become much larger. And that would be inducing a kind of a curvature. So I can play with different curvatures first. And I will play with different curvatures, and once I get into this exponential thing I will explain it thoroughly, because this is not going to be an exponential distribution like that. I would have to take this to be the exponent, not the base of the exponentiation. Okay, so I'll talk about that later, but the easy quick fix here is to take values between 0 and 1, exponentiate, and then do the math. So times whatever, 3000 and plus 200. And now what I have is that I can change this exponent and I will always retain this range. You see, because the point is that no matter what exponent I take, range 0 to 1 will always remain the range 0 to 1 for whichever exponent. Okay, because 0 to power of anything is always 0, and 1 to the power of anything is always 1. Okay, so this is a kind of a robust way of allowing yourself to play with the distribution of these filter frequencies without worrying about the range too much. Okay, so this is bloody hell. So it's definitely distorting. But what you also hear is that there's many more high frequencies. And I could actually say, well, actually at this stage it is too many, so I can decrease this exponent. Let's see what happens at 1.2. Okay, and because it's so neat and amazing, I can quickly increase this to 35. Okay, I don't hear much difference there. So what you get here, let's avoid distortion. So what you get here is that now we have a density of filters which is such that I get a very similar timbre each time. So if I have only 5 each time I run it, I get a slightly different one. Although it is a bit suspicious. Let's just print this array as well. I wonder what it actually becomes. Oh yeah, that's the suspicion. There is something wrong here. I believe it has to do with floating point values here. Is that? There you go. Sorry. So now we're getting a decent array. Cool. Let's now try with 53. Bloody hell, I just wanted 35. Let's reduce the amplitude dramatically. Okay, well, that's getting somewhere. So let's just see if this has become something useful. Let's take it to the power of 4 and get more. Okay, so the thing here is that if you take a power which is higher than 1, then you're getting an exponential curve. If you can visualize that, you understand that you're pulling down the frequencies in the middle. So 1 remains 1, 0 remains 1, and the higher the value, the more you're pulling them down. So now we get more bassy things happening. And if I take an exponent which is lower than 1, then I'm actually using the kind of a square root looking function. Great. Okay, I'll leave that there, and then what I also wanted is random arrays of oscillators. So let's quickly do that as well. Let's reuse this exponential distribution. Let's reduce the amount of oscillators. Let's take 10. And let's make these of higher frequency. Let's go between 1,000 and much more, 8,000, and well, I don't know about the distribution for now. Okay, so each one of these will have an envelope. Let's use a common envelope, make this a bit quicker. So what I can do, let's use something that will potentially create aliasing as well. So we get inharmonic components. So now we're kind of being clever about using aliasing. so LF pulse, audio rate, and then you've seen it last time. I can actually just put an array in there and that should work. And actually I can make the width a bit less so we get even more high frequencies out of that. And then I will multiply this with the percussive envelope, which I will make shorter, because I want this to kind of create the crashy attack bit more than anything. Okay, let's hear that. Well, I'm not totally impressed. Let's take more oscillators. Let's take, let's pull down the distribution like that. Now it's quite electronic-y. Let me just play with this a bit more. Well, that's what it is. Let's just add the two together. So we have those oscillators, sorry, those filters and these oscillators in tandem. F and K. Oops, and it's dead. What's happening here? Okay, so I was trying to play this array. So the F is that, and then well, not necessarily a Cymbal sounding thing, but definitely random arrays of oscillators and filtered noises. Great, thanks for following and see you soon. Bye bye.